Hey, what's up? It's your boy, Chef Boyo Robbie. Your food sucks. First and foremost, I know it's been a second, but I've been really busy. Let's just, you know, beating around the bush. I've been really busy. This will be the last video that I'll be uploading in this current setting. Uh, Video should be better in the following weeks. For one, I'm moving again, and yeah, I'm doing some extra stuff. Let's turn you down just a tad bit. Okay. So I'm going to open up with a bit of a retraction from the last video that I did. Not a retraction, but more so a correction. You may not be able to see that. Let me turn you around just a little bit. Actually, it's probably difficult to see anyway. Alright, so last problem that I did on the video, or on one of the other videos for electrodynamics. Yeah, first of all, yeah, that's what I'm opening up with. I'm doing Zangwill's modern electrodynamics. I did this commutator problem with the L operators dotted with two constant vectors in A and B directions, and I made this bit of an error in the sense that I jumped from having some Levi-Civita symbol coming out of the commutator. You saw the Li minus blah blah blah, the commutator relation. Then I said there's this. I took this relation from the book, where there's a commutator and there's a minus IH bar LM. The IH bar comes from quantum mechanics. And then I jumped into dot product. Well, you can jump into dot product, but in reality, what the dot product comes from, or the reason why the dot product is the answer, is because when you move the Levi-Civita back to where the Dirac Deltas are, and the and the directions that the Kronecker deltas are actually non-zero. Well, the directions in which the Kronecker deltas are non-zero, whatever the fuck. You have this minus sign that comes out of the commutator, changes the direction that the Levi-Civita is now positive. You're putting the M here. This is indicating a direction. Your M is now indicating a direction in which AJ and BK, the components of this new vector, have been crossed. And LM is already there. That's how you can make the assertion that, okay, I have a dot product somewhere between this cross vector, which is all of this stuff plus the EM direction, with the LM in its EM direction, which is by definition a vector, which you can't see, but the vector is the sum between the individual components with their corresponding directions. Just wanted to make a clarification. That took a bit longer than I wanted to for that clarification, but whatever. The rest of these videos, I've had a couple people, look over my my raw footage, and they were like, just make it a little bit more fun. Well, you're really uptight about it. I'm like, I'm really uptight about math, Math is fun and all, but it's business, man. Math is business. So I'm now gonna I've done a lot of problems. This is the modern. You can't see how many pages, but this is the modern E&M book that I have for problems so far. So I've done just about all of them from chapter 1, most from chapter 2. I'm going to finish up chapter 1 and then go straight into chapter 2. And, chapter 2 really hits a little bit on chapter 3. Because chapter 2 of Zangwill's book is this introduction to the time-dependent charge and current densities. Personally, I think that could have very well been left for the corresponding chapters in like 4 or 5 for the current 4 or 5 for magnetism, and the time-dependent charge for chapters 3 and 4 of electrostatics and electrodynamics that he goes into. But hey, it's not my book. I just solved the problems. So I'm going to finish up chapter 1. I'm going to finish up chapter 1 with this not Kronecker delta, but Dirac delta style like problem, in which Zangwill asks us to evaluate or prove that this function, or this limit, this limited function, this limit function, this function with a limit, is actually, or can actually be, a delta function. And this function by itself is called a sinc function. It's a special little sinc function because it has the 1 over pi, so it's a 1 over pi sinc. Actually, I think it's. Correct me if I'm wrong, but I think that's what it is. No, it's not sine, it's sinc. Regular definition of a sinc function. First of all, I don't think I'm introducing the music. This is Bowley Mix's mix that he put up like 4 months ago. I like hip hop. I like classical music. I find classical music to be better suited for problems, but you know, I like to mix it up too. Anyway, sinc function, yada yada yada. And so we have to just evaluate whether or not it's a Dirac delta. And if you don't know how to do that, well, I would suggest looking for math methods books that actually talk about Dirac deltas. And the whole point of what a Dirac delta does is that the definition of a Dirac delta, and then I'll explain what it does. This is a general Dirac delta. It just picks out an individual point where the function, or where the Dirac delta is 0, and it just makes that function, you know, that point. That's dumb. That's a dumb way of putting it. Okay, so you see this. This is the way of. Let's draw the picture. So you have a function, some really weird curve. The Dirac delta function looks like this. It's a peak, so it's an infinitely high peak with negligible width. So it's all this, except negligible means that it doesn't have any brown in between, but whatever. We're gonna say it is for the sake of argument. And this is our function f of x. And so when you integrate through all of space, in this case throughout the entire x direction, the Dirac delta takes that point where it's 0, in this case it's x equals 0, and it makes that function, the intensity of that function, where the Dirac delta is equal to 0. And that's the definition, or that's what a Dirac delta function does. So the whole purpose of this exercise is to get us to think about Dirac delta functions, because they're going to be very important in terms of like charge densities and taking derivatives of position vectors, or the changes of position vectors, etc. So how do we prove it? Well, we do exactly what we did. We said that some function goes to f of 0 where the Dirac delta is 0. So let's take some random function, f of x, and let's multiply it by d of x. I mean, capital D of x, and integrate it along all of space. So how do we do it? Well, this was my trick. I took u is a function, well, x is a, well, u equals mx. So therefore du dx equals m, or dx equals du over m. I'm going to try to write more or less on this side so you guys can actually see. Easy peasy. Easy peasy. No, I don't have any dust in my nose. Oh my god. Alright, so change of variables. X is u over m, so f of u over m is the new function. D of u over m is sine of u divided by pi. X is u over m, so m is up top, u is up bottom. Sexy, sexy. Times du over m. M's cancel. Easy peasy. And then we also have the limit, so don't forget the limit. The limit as m goes to infinity. Normally this function, if you don't know, m is increasing without bound, but the thing about sine of a function like that, well, what does sine do with increasing frequencies? Well, it just it changes the points where x is going to be 0. Not pertinent to the problem, but whatever. It could have been if we chose to go another route as opposed to the substitution method. Another way of doing this could be you could have gone a series route. I wouldn't recommend it because I started to and it was bullshit, and then I said, oh look, change of variables. Why? Because m is going to infinity. And it's too much work. It's too much work doing the series for sine, and then you taking the series off of x. You know, it's possible, and actually, for some people, it might be easier, but I didn't feel like it. Anyway, so where was I going with this? Oh yeah, I know where I was going. So we're going to take the limit. Take the limit of u over m. Sine of u, and again, why this method is a little bit easier is because we have a function here, a sinc function that does not depend on m, and then we have a function over here that does depend on m, but m is going to infinity. This is a regular function. I mean, I didn't say it up here. I said it's an arbitrary function, but let's say it's an arbitrarily regular function. So we don't really have to worry about any like discontinuities at m and things like that. Please go ahead, evaluate this limit. We said as m goes to infinity, u over m goes to 0. So then we have an f of 0 divided by pi. And here you go. Bada bing, bada boom. Du. What's that integral? Hell if I know. I'll be totally honest with you. I looked it up. I looked up the Laplace transform. Actually, what is this? This is an odd function over an odd function. Odd function over odd function is an even function. So it goes from 0 to infinity. Looked up the Laplace transform of this. Where can you see? Laplace transform. If you don't know what Laplace transforms are, don't worry. I'm going to be going over a lot of this. I realized that after doing some of the problems from like chapter 3, chapter 2, chapter 3, that I'm going to have to go over Laplace transforms myself. I did do transformation. I took a class in transformation methods, but that doesn't mean that I remember all of them. So I'm going to have to go back and do some of that work. I'll do videos on them as well, but I'm also going to be doing videos on differential equations, so you'll be able to see them in like an application point of perspective, as opposed to just a pure me teaching Laplace transforms and well, Laplace and Fourier transforms and those sorts of things. Fourier is a lot easier than Laplace, but to each his own. So this is 2f0 over pi. This Laplace transform actually goes to pi over 2, I believe, which then well, not goes to, but is pi over 2. Therefore, the answer to this problem is indeed f of 0, which then makes it a sufficient Dirac delta for an arbitrarily smooth function f of x. So easy peasy. No, well, not really easy, but you know, it took a little bit of took a little bit of looking up for the Laplace transforms, and you know, just sitting down and thinking about, well, what's the best way of approaching this sort of problem? Is it going to be a series solution? Is it going to be a direct, you know, a direct integration? And I just found that direct integration was a lot smoother. All right, so we're going to go ahead and jump right into chapter 2. Chapter 2 hits you with, like I said, those time-dependent functions. Talks a little, well, not a little bit. Talks a lot about just, you know, forces, magnetic forces, electrostatic forces, electrodynamic forces. Goes into microscopic phenomenon for electrostatics and that sort of thing. One of the problems goes like this. We have two forces, F1, and F1 has only a magnetic field. So you've got some charge going at some velocity v1, and the force is then crossed with another a magnetic field v1. But we also have another force. We have another force F2 acting on the same charge. Relative to that, B field is going at V2 in some direction. It does not have to be in the same direction as F1 or V1, and it's affected by some other field. I'm sorry, these are the same fields. Okay, so we have two forces. One charge, and relative to the B field, the charge has two separate velocities. What's the total force? I think that's more or less what it's asking. No, it's actually asking us to find what the B field is. Or can we determine what the B field is from this information, from these two forces? And the first thing that I thought of was like, alright, so we're going to have to get the B field by itself. If we're looking for the B field relative to these under these conditions, we got to get the B fields by themselves with respect to these two forces. And then figure out what the B field is with respect to these two velocities. So how do you do that? Well, easiest way of starting is to not make the forces zero. And how do you, well, you make the forces zero by dotting them with, you know, vectors that we know are already perpendicular. So if we dotted F1 with V1, then we'd have a 0. If we dotted F1 with B, then we'd have a 0. Same thing for F2, respectively. So let's cross it. Let's cross F1 with V1. And from chapter 1, or from the chapter 1 videos, we know that the result is going to include some back cab relationship, which is, actually let's make this a little bit more back cab. V1 dot B V1 minus cab it's the same thing, isn't it? Yeah. That's right, right? That's right, right? That's right, right? That's right, right? Yeah, no. Back cab, AB. So AB is B. Yeah, that was wrong. That was wrong, right? Okay, so first and foremost, we know that the force is we only have a force when V is perpendicular to B. That's magnetostatics. So this is going to be 0. If we do the same thing to F2, V2 cross F2. I know that the video is a bit blocky once we get to that point, but you know, bear with me for a second. We have the same relationship. We get minus v2 dot v2, not v, but b. And I'm going to stop writing b as a function of r because we kind of know that now. So force v1 has to be perpendicular to b. v2 also has to be perpendicular to v, but v1 and v2 do not have to be perpendicular. I'm going to think about that one because that may be true. Yeah, I'm going to think about that one. Yeah. So we get v1 squared minus into b, and then we get minus v2 squared with the b. Okay. Okay. Well, what do we do next? What do we do next? Well, Rich, like we said, we had to get b by itself. Well, we kind of have that, don't we? We have that b is the sum of these two things, right? We get b is minus v1 cross f over v1 squared, or qv1 squared, minus v2 cross f2, f1, f2, two separate forces, over qv2 squared. Okay. So this is what we're going to do here. This is what we're going to do. My notes get a little bit sketchy in the sense that okay. So what was the other objective? The other objective was now we have to find b with respect to these v's. How do you do that? Well, we can start off with a dot product. A dot product will get rid of v2 and will give us a dot with this. Will give us a dot with this. If we dot it with v2 with b, let's go ahead and just we'll get rid of the top information. We have a function of b, so we don't really have to worry too much. Yes, I have a magnetic eraser because I'm slow like that. Let's get rid of you. Cause I'm slow like that. Cause I'm slow like that. Gotta get that B by itself. That B by itself. We gotta get that B by itself. Yeah, 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 yeah. Alright, so we're gonna dot V. Let's do V1 because I think that's what's in my notes. We dot V1. V1 would be. And what do we get? We get V1 dot with the negative of all this stuff. We're taking, just factor out the negative. V1 cross F. Well, that's a no-no. That's 0. And then we get V1 dot V2 cross F2 over QV2 squared. Does this help us at all? It's a good question. I don't know. Yeah, it's a very good question. I don't know if this helps us. Some people are saying, well, why the fuck did you do this problem then? I did this problem because I thought I had it. I thought I had it in my head. My notes are really sketchy because I'm thinking I've got V's, V2s, and F1s where I think V2s and F2s where I think I'm supposed to have V1s. But let's flow with it. We got a dot product with a cross product. It's going to come to me. So we got a dot product with a cross product. We can always go back and look at our relations and see exactly how that'll help us, if at all. Because this is the reason why I keep notebooks, is to keep me honest about the actual relationships, because I think maybe we have a relationship that I'm not using with the dot product and the cross product. Because what I want to do is I want to substitute that back into this equation somehow. I want a relationship between F2 and V2 that includes eliminating the V's, or at least one of the V's, so that I can get, you know, something by itself. And I guess it's coming down to this is what we got, that's right. And then I have this relationship. V1 cross F1. I apologize. I really do, because this is looking a little bit more ridiculous than I thought it would. I might have to come back to it. I might have to come back to it, because I might be missing something. What I'm thinking is I eliminated something that I shouldn't have eliminated, which very well may be the case. I think it's coming down to the v1.br part. That may be it. Is that 0? Is that really 0? Is the question. But I can't just factor that out. You know what? Let's do that. Let's do that. Let's start over a little bit. So this is probably going to be the last problem. Then I'm going to do another video, and I'm going to upload the results. So I started here with a B function that was a cross product between V1 and F1. Okay, and I said that V1.B is 0. That's not true. No. The force is the cross product between V and B. But V doesn't have to necessarily be, V.B doesn't necessarily have to be 0. Okay. It's a good start. It's a really good start. So B subtract, so what was B originally? What did we originally have? And this is going to correspond to V1 and V2. So V1, I'm going to stop writing vectors because we know what they are. F1 equals, you can tell I'm a bit frustrated. So we had the back-cab relationship between V1 dot B, V1, minus V1 squared B. Cool. We're going to divide by Q, and then subtract this on the other side, and then divide by both sides. Okay, so V1 cross F1 over Q. This is going to be minus, plus, well, let's just do it, plus V1 dotted B, V1 over V1 squared. And this equals B. Same thing for V2. Okay. So we have a function by itself with respect to V1, but we also have a second function by itself with respect to V2 and F2. I think what we want to do is get rid of these F's. That's really what we want to do. There we go. I think we're cooking with gas now. Now dot that with V. Dot that with V2. Dot this with V2. We get rid of this shiggity up here. Do something for me, board. Just keep standing. It's the last day. B dot V2, well, B of V1 dot of V2 equals minus. We can get rid of the minus by switching the directions of the cross product. So V2 dot F1 cross V1 over Q V1 squared plus V2 dot V1 dot B over V1 squared. Ah! We found it. We found it. We found how to make this one equation. BV2. BV2. Why couldn't I do that before? I think I could have. But I'm not sure it would have been correct. For one, what did I have? I had just this part with just this part because I said that V1 and V2 were 0. I had no way of relating these two relationships here. There was nothing that I could have done. The dot product with V2 wouldn't have given me a cross between V and F2. Wouldn't have given me a V2 squared anywhere. So I would have had I was stuck. I was stuck there. That's the reason why it wouldn't have worked. But physically speaking, why it doesn't work is because this isn't necessarily 0. It has no force. This is no force. You take a B field, a very rudimentary and very unrealistic B field, and you have a particle moving with some velocity v in that direction. There's no force, but that doesn't mean that the dot product is 0. It does have some magnitude. They are directions. They're directed fields, and in this case, it's this. This is the directed field of B and V2 with respect to predominantly V1. We can do something really nutty. What can we do that's nutty? We'd have to put all of this into this function for V2.B or B.V2, and that would be your function for B. But is there a way of simplifying this? The way of simplifying this is that we say that we could say that F1 and V1 are, F1 cross V1 is perpendicular to V2. That'll save us some time. But will that help us in the long run? I don't see why it couldn't. I think this is a bit too complicated. F1 V1 is perpendicular to V2. It doesn't exactly help us too much. We could also say that V2 and V1 are perpendicular, which makes a good amount of sense. Does it really? So this is some vector V, and this is V1. I'm assuming for the sake of argument that they're perpendicular, so that they receive two different forces from B. You have the force 1 and force 2. Does it make sense to say that they're perpendicular? You get a force. It's perpendicular to both, so it's something like this. The force is somewhere like this for V2 and somewhere like this for V1. And so those are your forces. So you're saying that the forces are also perpendicular, because if these two are perpendicular and they're dotted where they're crossed with this, then the forces have to also be perpendicular. It creates a new direction. Well, a new direction triplet. I don't see why not. This, you could say that this is 0, that they're perpendicular. This works. But actually, I think that is exactly what I was saying here. F1 cross V1. No, F1 cross V1 would then also be in the same direction as V2, or it possibly parallel to V2. So this works. To simplify this this expression, you say that V2.V1 is 0. You put all of this back into the second equation that you had for B, and there you go. You have B as a function of either of variables that we know. Yeah, we would have B as a function of variables that we know, because you can't have B in itself. That works. Cool. Alright, that's going to be the end of the video, guys. I'll make a part 2 in a couple minutes with something else. More problems from chapter 2 / chapter 3. This was a shorter video than the last one, but hey, stay pimpin'. Thanks for watching. See you.